Look at a standard power plant, and you will almost certainly see a massive cooling tower venting thick clouds of steam into the sky. That cloud of water vapor represents raw, uncaptured heat energy bleeding away into the atmosphere. By expelling that heat rather than utilizing it, standard generation facilities lose more than half of their fuel's potential energy before it ever reaches the grid. To solve this specific mechanical loss, engineers developed the cogeneration power plant, frequently referred to as a combined heat and power system. The mechanism works by extracting two distinct usable resources, electricity and thermal heat, out of a single fuel source simultaneously. Capturing the heat that usually escapes out of a cooling tower turns a massive environmental liability into a precise, measurable upgrade in performance. We can calculate the exact scale of that performance upgrade using a mathematical scenario drawn from the UGC NET environmental science exam. This UI ledger establishes the standard formula for thermal efficiency. We divide total output energy by total input energy, multiplying by 100. We establish starting parameters by feeding 60,000 gigajoules of fuel to serve as input energy. As the plant consumes that fuel, the system splits the resulting energy into two active streams. The first stream yields 30,000 gigajoules of captured usable heat energy. Simultaneously, the second stream generates exactly 5,000 megawatt-hours of electricity. To find our total output energy, we naturally try to add the heat to the electricity. But we immediately hit a mathematical wall. We are trying to add gigajoules directly to megawatt-hours, creating a unit mismatch that brings our calculation to a complete stop. This animated diagram isolates the anomaly holding up our ledger, the 5,000 megawatt-hours of electricity. To create a uniform equation, we have to translate those megawatt-hours into the exact same gigajoule standard used by the rest of our inputs. We bridge that gap by multiplying our 5,000 megawatt-hours by a specific conversion multiplier, 36 times 10 to the power of 8, scaling it to the joule level. The math resolves smoothly. That initial electrical output is equal to exactly 18,000 gigajoules. Now that our units match perfectly, we can combine our 30,000 gigajoules of heat with our converted 18,000 gigajoules of electricity. Together, they yield a unified total output energy of 48,000 gigajoules. Standardizing our measurements removes the mathematical roadblock, revealing the true, combined scale of resources the system manages to capture. This animated diagram brings us back to our fully assembled thermal efficiency formula, with all variables strictly operating in gigajoules. We execute the final division, 48,000 output divided by 60,000 input, multiplied by 100, resolving cleanly at 80%. Standard power generation frequently wastes 50 to 60% of a fuel source. Retaining 80% of an input's potential energy demonstrates a significant mechanical advantage. Instead of venting massive amounts of its initial value into the dark sky as steam, the plant puts the vast majority of it to work. This mathematical proof from the UGC NET exam illustrates how effectively heat recovery can mitigate industrial waste. By utilizing a much larger share of the energy in a single fuel source, cogeneration provides a high-efficiency blueprint for improving industrial resource management.